All right, so let's talk about the last part of this. So we've talked about how you can move the graph up or down or left or right. We have talked about how you can reflect the graph. So you can reflect the graph top to bottom, or you can reflect the graph left to right. The last thing you can do is stretch or compress. So you can either stretch it out and make it taller, or alternatively stretch it out and make it wider, or you could make it compressed. So you could compress it and make it shorter, or you could compress it and make it thinner. So again, the same general trend is true for a lot of these. If you're going to have a vertical stretch or a vertical compression, that's going to come from a value applied to multiplied by the entire function. Just like if you put a negative on the whole function, it goes vertically. If you add or subtract something from the whole function, it goes up or down. If you multiply the whole function by a value, it will either stretch it or compress it. There's a couple different things that can happen. So if your number is bigger than 1, such as, for instance, 2, it'll stretch it. So if you multiply the whole function by 2, it's going to stretch it by a factor of 2, and it will be twice as tall. If it's between 0 and 1, it will be compressed. So for example, a number like 1/2 is between 0 and 1. And if you have a number like 1/2, it will make the graph half as tall. So that should be maybe reasonably straightforward. If it's less than 0, that's actually going to be a negative number. So negative would reflect it. And then like if it was a -2, for instance, it would reflect it and then stretch it vertically. So it's twice as tall. It's just, it would like be going down instead of up. So what you would need to do is identify the value of A, multiply all the range values by A. And then again, if it's negative, you would have to reflect it about the x-axis. So if you have a negative value, it's being reflected along with being stretched. So here they give us a graph. The function p of t models the population of fruit flies. So our goal is to basically make one that is twice as large. So our goal is to graph, we'll call it, I don't know, f of t, and that'll be equivalent to 2 times p of t. So we basically want something that's going to be twice as large. So especially with the graph that's right here in front of us, this is not going to be too terrible. Here we have a value of 1. We just double that so that at the original graph, we're going to have a value of 2. This point is originally at 3. If we double that, it's going to send us up to 6. And then we will still have this kind of curvy thing here. It'll be the same general shape. This is 2 tall, so we're going to make it 4 tall, and it's going to be just right there. And then again, we'll have a straight-ish. That's my best attempt at drawing something straight. But anyway, we have this kind of straight-ish line that's connecting that. And then this is at 0, which means it's just down all the way at 0. Fun fact, 0 times 2 is still 0. So this example was actually pretty short and sweet. Since you're doing a vertical stretch of a factor of 2, you're making it twice as large. So you're just going to make each y value twice as high as it was originally. You're just multiplying the y values by 2. If you do something inside with the x, that's going to be a horizontal stretch or a horizontal compression. So again, Anytime you're inside with X, it's going to have an impact on the X direction. So it's going to squish you horizontally or stretch you horizontally. Now, just like before, how like if it's minus, like if you're moving left or right, if it's -2, you actually go to the right by 2. You do the opposite of what you would expect. Normally minus, that's negatives are on the left side, but you actually go to the right when you're inside with the X, because X is always the opposite of what you would expect. Similarly, if you have a B value of 2, it'll actually compress it by a factor of 1 over B. So what that means, if I have f of 2x, that will actually be 1/2 as wide. It does the opposite of what you would expect. If you have a value between 0 and 1, such as 1/2, it'll also do the reciprocal. So if you do f of 1/2 of x, that is actually going to be 2 times as wide. So it's always the reciprocal. It does sort of the opposite of what you would expect it to do. And that's of a kind with what happens with the, where you move them side to side with the shifts. Just like a minus is actually going to send you to the right, a 2 is actually going to make you 1/2 as wide. And then just like before, if you have a value that's negative, you're going to have a reflection happening at the same time if it's like super complicated. So here they give us a graph and they say, write a function that's going to relate g of x to f of x. So basically, what we're going to do, here you'll notice this is the point 6, 4. This is the coordinate of this point originally. This point where the corresponding point, this is 2, 4. So basically the question is, how do you go from there down to there? And the answer is it's 1/3 or divided by 3 basically. So if you take 1/3 times 6, or if you take 6 divided by 3, that'll shrink you down from 6 down to 4, or I'm sorry, 6 down to 2. I don't know what I was saying. So if I take f of 3x, that will be equivalent to g of x. Since I'm dividing by 3, I actually need to do the opposite, which means I would have to multiply by 3. Or, since it's 1/3, you have to have the reciprocal of that, which is 3. So that would be how you would go from the one function to the other function. So this last bit here, if you have a bunch of transformations all together, how do you combine them? Well, so the first thing you would do when combining vertical transformations, vertically stretch and then vertically shift. So you would vertically stretch and then you would vertically shift. If you're combining horizontal transformations, you'd first horizontally shift and then you'd horizontally stretch. And here you notice you have to divide by the value of b right here. You don't just move by the value of h, it has to be h divided by b. The reason that's happening is that you would basically have like b times x minus h over b. I don't know if that helps or not, but that can get quite complicated when you're trying to horizontally shift and horizontally stretch at the same time. If you're combining horizontal transformations written in this form, so here they say horizontally stretch and then horizontally shift. This is kind of the more standard way to do it. It's a little more complicated because you're factoring out this B first, which is kind of what I'm up to here. But that usually makes the process a little easier. And it also makes it consistent with how you do the vertical ones. You do the stretches first, followed by the shifts, which is usually a little easier for people to do. Horizontal and vertical transformations are independent. It does not matter whether horizontal or vertical ones are performed first. So that's kind of a summary of some of these here. So here they say, sketch the graph of 1/2 x plus 1 minus 3. So here's what we're going to do. We've got this formula right here. So here's what we're going to do. We've got f of 1/2. I'm going to factor out 1/2 and make this try to make this a little larger. That was way too large. All right, so we're going to do 1/2, and then we're going to have x plus 1 divided by 1/2, which for those playing the home game, 1 divided by 1/2 is the same as 2. So this is f of 1/2 x plus 2, and then minus 3. So what is happening with this? This is going to be 2 times as wide. This is going to move it left 2. This is going to move it down 3. So you do the stretch first. So you do the stretch first. And then you shift second. And then we'll do the vertical last. So you always do the stretches first, then you do the shifts. And then just make sure you do all the horizontal stuff first and then do all the vertical stuff. So what do we have here? So we're going to make this thing twice as wide. So that's going to go out to -4. This would stay where it is. And then this would go out to +4. So if we stretch it, I want to draw it as a dotted line first. So if we stretch it, we're going to end up with the kind of red dotted line first, where it's the semicircle that's kind of stretched out so it's wider. So it goes to -4 and +4, but then it's not any taller than it was originally. Then what we need to do is we need to shift everybody left 2 spots. So maybe I'll do that in yellow, maybe. So everybody's going to go left 2 spots. So we're going to go left 2. This one's going to go left 2. This one's going to go left 2. So we end up here. And then we would have like a semicircle kind of like that. And then the last thing that we're going to do is we're going to go down by 3. So, I don't know, maybe purple. So then we're going to go down 3 from where we left off. So we're going to go 1, 2, 3. There you go. We're going to go 1, 2, 3 and end up right there. And then this one, we're going to go 1, 2, 3, and we end up right there. So then our final graph is going to look something like that. So we stretch it first, Then we move everything left by 2 spots. Then from there, we move everything down by 3. So that's it. That is the end of that section. So I'll do the attendance here in just a moment. We'll